este tribunal, formado por los doctores Dieter Boer y la doctora Elizabeth Capón García y Luis Puigneró Corbella. Se reúnen hoy para juzgar la tesis doctoral que presenta el señor Robert Brunet. Tiene usted alrededor de 50 minutos para decir lo más relevante de sus aportaciones y luego a las preguntas que comunican.
Good morning, everyone. Welcome to my PhD presentation. I am Robert Brunet, and in the next 50 minutes, I will present my thesis titled Optimal Design of Sustainable Chemical Process via Combined Simulation and Optimization Approach. I did this thesis in the group Suscape of the Department of Chemical Engineering in the University of Rovira i Virgili under the supervision of Dr. Laureano Jimenez and Dr. Gonzalo. I divided the presentation in 5 blocks: the introduction, the bioprocesses, thermodynamic cycles, biofuels, and finally the conclusion. In the introduction, here I will present the aim of the work, the main objective, and the background of my thesis. The traditional performance in process system optimization was to reduce costs or maximize profit. However, nowadays, a new trend has to also reduce the environmental fee. Therefore, we will focus in this thesis in reducing the cost as well as the environmental fee. The aim of the work is to apply systematic tools to achieve reduction in the economic and environmental costs of chemical processes and to develop a systematic method based on process simulation and optimization tools. The key bases of my research topics are the chemical process, which is the case of a study that we will treat. The economical evaluation and life cycle assessment are the indicators that we want to optimize, and the mathematical programming and process simulation. They are the tools that we will use. All of this with a common objective, the multi-objective optimization for sustainable chemical processes. Here we have a typical chemical process, and the problem that we have is, given are the demand and prices of final products, the cost parameters, the time origin, the thermodynamic properties, the performance models of the equipment, and the life cycle assessment, the goal is determine the optimal process design, which means the optimal operation conditions, the optimal type and size of units, and the topology of the plant. The first question is how to measure the economical performance. We use the conventional economic models, and in some cases we take one or other economic analysis. The net present value, the total capital investment, or the operating cost are used in this thesis. And how to measure the environmental performance. This is newer, and we use the life cycle assessment from cradle to grave and following the ISO standards. The life cycle assessment is divided in 4 phases. The phase 1 is the goal and scope of the process. The phase 2 is the inventory analysis. The phase 3, the impact assessment. And the phase 4, the interpretations of the results obtained in the impact assessment. The methodology is expressed with continuous variables and is the sum of the direct emissions plus the waste generated plus the raw materials plus the operation phase and the construction phase. We use, in most of the cases, the indicator 99, which is divided in 11 different indicators or in 3 damage categories. The damage categories are damage to human health, damage to ecosystem quality, and depletion of natural resources. The mathematical programming is one of the main of this thesis, and here we will present the background. In mathematical programming, we have continuous and integral variables, and we have linear and nonlinear equations. When all the variables are continuous and all the equations are linear, we have linear programming. If we have some nonlinear equations, we have nonlinear programming. In the case that we have continuous and discrete variables and linear equations, we have mixed integer linear programming, and the most complex case, which is the case that we are solving in this thesis, is the mixed integer nonlinear programming, when we have continuous and discrete variables and linear and nonlinear equations. This is the typical formulation of mixed integer nonlinear programming. And here we have the objective function, the process equations, which are the mass, energy balances, and thermodynamic properties, the nonlinear equations, which are the sign specifications, the continuous variables, and in our case are the flows, the operation conditions, the size of the equipment, and the discrete variables are the existence of process units, the stages in a distillation column, or to choose one equipment or another. In order to solve these problems, we need advanced customized solution methods. Additionally, here, in most of the cases, we say previously that we solve in the economical and also the environmental indicators. Therefore, we have multiple objectives. How we can deal with multiple objectives? In this work, we use the epsilon constraint methodology. We have here the same MENLP as before, but with multiple objectives. What we are doing is take the objective and pass this objective as a constraint. And then we create a new problem with a single objective. Additionally, in most of the cases, it's not possible to obtain the same minimum of the cost and the same value as the minimum of the environmental impact. Then what's happening here is that this is the minimum cost solution, and this is the minimum environmental impact solution. And we are calculating the solution between these extreme points, the optimal solutions between these extreme points. We'll explain in the next blocks how we calculate it. Finally, the last slide of the introduction is why we are using simulation optimization instead of the simultaneous approach. Because until now, chemical process optimization were based on simultaneous approach, which means formulate an algebraic model in explicit form and solve it. Most of the cases, this work was doing in GAMS or in MATLAB. However, in process design, these models were shortcuts, were very simple. They could not describe very well what's happening in the plant. What we're doing here is presenting a sequential process simulator. It's more difficult to optimize, but we can apply the technologies that we have now and the speed of the computers, and now we can deal with these kind of problems. Then here I will present more or less how it works. We have an MENLP problem. An MENLP problem, in most of the cases, you have to solve in two sequences. You have to divide the problem in a NLP, where you will take the continuous variables, and the linear and nonlinear equations, and a master MELP, where you will have the discrete variables and linear equations, without nonlinear equations. Then we first solve the NLP. We have MATLAB as executing approach. We connect MATLAB with the process simulator. Could be Aspen Plus, Aspen HYSYS, SuperPro Designer, depends on the case. We use one or the other. We integrate this with an index calculator, because in most of these process simulators, we cannot calculate the cost that we want, or we cannot calculate environmental impact. Then we integrate with the index calculator in MATLAB, and we finish the loop with the NLP optimizer also implemented in MATLAB. With this, we iterate and we obtain the optimal solution of this NLP problem. With this optimal solution, we create a master problem. The master problem is solved in GAMS. And then there is an integration between these two problems to find the optimal solution, the optimal design, the optimal topology of the plant. Then, now we are moving to block 2, the optimization of bioprocesses, which is the first case of a study of this thesis. In this work, we present 2 articles. In the first one, we focus in the economic optimization of a bioprocess, and was published in Computers and Chemical Engineering. And the second article, we focus in the economic as well as the environmental optimization of a bioprocess, and it was published in Industrial and Engineering Chemistry. The first question is why we choose bioprocesses as first case. Well, bioprocess is a type of chemical process that produces biochemical products, antibiotics, proteins, amino acids, from microorganisms or enzymes, living cells, from living cells. Then they produce a high value product, and there is a lot of competition between among the different companies in the prices of the product. Then there is a clear need that they have to optimize their process to be more competitive in the market. The aim of the work here will be then develop a mathematical programming method for the optimal design of bioprocess. The bioprocess that we take, it was the lysine production. Lysine is an amino acid. This is a typical fermentation process. It's modeled in SuperPro, and we have the raw material preparation, where the main raw materials are the threonine and glucose. We have the fermentation in the bioreactor, where glucose and threonine reacts to produce lysine, biomass, and we have the downstream, where the biomass and the water is removed from the main product, the lysine. The production of this plant is not high because normally in bioprocesses or in this type of products, they don't have a very high production. Then we were working in this, and we find a problem or a challenge. At the beginning, we were expecting to have an MENLP problem. However, the bioreactor is described by differential equations. What means? That it's not possible to solve an MENLP problem. Then what we formulated as a MIDO, as a mixed integral dynamic optimization problem. We have the objective function, the set of differential and algebraic equations, the initial conditions, the enforced conditions that must be satisfied, and the time invariant equality and inequality constraints. As you can see, this formulation is much complex than the one that we presented in the block 1. Here I will present the algorithm that we use. What we are doing is first solve an NLP with a fixed topology. What means with a fixed topology? Without discrete variables. The number of reactors in parallel, which equipment we choose for the biomass removal are fixed. Then, with this solution, we will create an MELP. What we're doing is to find a new topology of the plant. And then we solve a new NLP. However, this NLP is a little bit tricky. Why? Because it has differential equations. Then here we have 2 methods. One is do it by orthogonal collocation, and the other is first solve the set of differential equations, and with the results pass it to the process simulator, and then the reactor of the process simulator will work as a conversion reaction, not as the complete reaction kinetic that we have. When we solve the NLP, we don't have yet the optimal value because we apply a termination criterion evaluation. The termination criterion evaluation that we are using is the NLP worsening, which means if the new solution is better than the previous one, we will solve again an MELP and another NLP.